resorting to companies are now resorting to heterogeneous hardware, and this is why you see people using many GPUs, especially for machine learning, TPUs, but also FPGAs. And I'm going to focus on what is the role that FPGAs can actually play in this hardware evolution. And then finally, the demanding workloads. This is also something that sometimes people forget. Behind all these changes towards cloud computing and hardware evolution and so forth, there is an important aspect that is what we try to do with these platforms is also changing. Of course, today there is a lot of things that are related to machine learning and artificial intelligence and running neural networks and so forth, but not only. We have huge amounts of data that have been processed not only for machine learning, but also in traditional ways. And these demanding workloads in terms of the amount of data, but also in terms of the latency and the speed that need to be processed, the volume of data and so forth, are actually converging into a very interesting situation. And I'll give you a few examples in a second so that you actually get a bit of a perspective for where FPGAs fit and what you can do with FPGAs in this scenario. So I will explain this a little bit from the point of view of databases. I'm picking databases because it's an area where I work and I know them well. However, everything that I'm saying can be said as well for distributed processing, can be said about machine learning, can be said about artificial intelligence. So this applies to a very, very wide range of systems. So if you take, for instance, databases, the three trends that I have just presented now are actually creating a very exciting research landscape. First, cloud computing forces you to completely redesign systems. What is a cloud-native database? So we come, if you have taken a database course, right? I mean, as part of your studies, you will have taken probably a very traditional course where it explains you how relational engines are implemented. Most of them actually run on a single computer. In the cloud, there is nothing like this. Today, the whole database industry is completely redesigning from scratch database engines, right? After 30, 40 years of sticking to the monolithic engine, is actually completely redesigning database engines from scratch because of cloud computing. And then if you have new hardware, the question is that how should a database look like? How is a database going to take advantage of a GPU? How is a database going to take advantage of a TPU? How is it going to take advantage of an FPGA? And then finally, the demanding workloads. Traditionally, databases use benchmarks that are TPCC, TPCH. TPCC is a transactional benchmark, TPCH is analytical benchmark, but this is not the top of where most of the attention is today in terms of data processing. Most of the attention today, as I said, is machine learning. So what are you going to do? Are you going to push machine learning inside the database? Are you going to do it outside the database? What are the best interfaces for actually doing this and so forth? So you see, these trends actually are not just something that you can say about where hardware is going and so forth, but these trends are having a very, very significant effect on one particular part of the software industry, that is databases. Now, exactly the same picture can be drawn about operating system, about distributed systems, about storage systems, about networking, and so forth. In essence, these three trends are completely changing the way we are thinking about computing, both on hardware and software. Okay? Now, so that you don't have to believe what I'm saying, I'm going to try to sort of give you proof of what I'm saying. And I'm going to give you proof of what I'm saying with empirical evidence. I'm going to give you 3 examples from industry. I'm going to focus on things that people do with FPGAs or closely related to FPGAs, so that we start focusing on what is the topic for the talk. And then I will talk a little bit about our work, about Enzian, that is a computer that we're building at ETH to explore different architectures and so forth. And then I will give you a very brief idea of a system that we have built also at ETH that uses FPGAs, so that you also get a bit of a picture for the type of systems that you can actually build for FPGAs and what does it entails to actually build such systems. Okay, all right. Now, if I have done everything right, I see the chat, and if you have any questions, feel free to type it on the chat. Otherwise, you can also unmute yourself. Since we are not a huge amount of people, you can unmute yourself and just tell me, and then you can ask a question, right? So feel free to interrupt me at any time. Otherwise, we will have time for questions at the end. Okay. All right, so then let's jump right in. So in industry, what I'm going to do now, as I said, is I'm going to give you 3 examples of hardware acceleration that actually are very much in use today. For some of you, maybe some of these things are known. For others, they are going to sound a little bit like crazy things, but please believe me, these things exist. These things are being done, and I'm going to explain you why they are done. So now, the main thing, and you're going to see a common theme, is that when we are focusing on data processing, as I said, I'm just focusing on data processing to make this concrete, not to talk about too broad a topic. In data processing, the biggest problem is, as the data becomes larger, is you have to move the data back and forth. You have it in storage, you have to move it from storage into the memory, from the memory to the CPU, to the registers, you do some processing, then you need to get the results back to the memory. From memory, you have to go to storage, and so forth. And if you do this in the cloud, of course, this becomes much more expensive because the cloud, the storage and the compute is disaggregated. So storage is actually somewhere else. You have to go through the network. So that is a big bottleneck that we have today. Okay. And the other aspect is that important workloads, they are no longer processing a single computer. Distributed processing is the name of the game. Whether you're considering something like serverless or you're doing machine learning and so forth, everything is very much distributed these days. So if you consider these aspects, data movement and the fact that things are distributed, you have to go through the network most of the time for everything that you want to do. That already starts giving you a few ideas of where you can actually use acceleration, where you can actually use hardware, where you could actually use hardware to improve things. And those are the examples that I'm going to give. Okay? So let's start with an example within a machine. So this is an SQL query. For those of you who do not know SQL, this is actually something that says select all attributes from a table T, where the ID equals 3. This is a very classic example of a query that goes over an entire table and just selects one tuple. This happens, for instance, if you're in a database for a social network, when you are selecting the profile for a particular user, you take the key for that user, and then you just retrieve that profile. Or you're trying to retrieve the telephone number of a particular person, or you're trying to retrieve the grade for the grade point average for a student out of a university database or something like this. So the problem with this query is that a database typically will read the table from memory, bring all the data to the CPU registers, and then will actually throw away all that data just to keep one single tuple, the one that matches the predicate that you have in there. So you actually realize the amount of data movement that has been involved in here. Okay, so this creates bottlenecks in memory accesses, in the data buses, pollutes the caches. Is a big mess. So Oracle, which is a database company, came up with something that I always consider very, very cute. What you see on top of the figure is the standard figure of a multi-core processor, where you see different cores. You see 8 sockets. Each socket has 4 cores, and each one of those sockets has an L3 cache, an L2 cache that is shared, an instruction cache, a data cache, and then there is an L1 cache in each one of the cores and so forth, and then there is an on-chip network, and then you see the memory. The memory is those green boxes that are outside the multi-core chip. Okay. What is interesting is that you see also on that figure there is an accelerator, and what this accelerator does, it is positioned between the memory and the on-chip network. And if you want to know what the accelerator does, you can look at the lower part of the figure, where I show just one aspect of this accelerator, because the accelerator does several things. It actually is also used for instance, checking pointers. It's used for security, to actually check that you're not going out of memory, out of bounds, and things like this. But the other thing that it does, it actually what Oracle calls, or used to call, SQL in hardware. What it does, it actually pushes the filtering of tuples, filtering of tables, and a number of other operations to that accelerator. The big advantage of doing this is that whenever you want to read a table, instead of bringing all the table all the way to the core, you actually do the filtering on the accelerator. And if you look at the architecture, it's very simple. It's very easy to realize that this has the big advantage that the data is going to be stopped. The data that you don't need is going to be stopped at the accelerator, and it's never going to get into your chip network, and it's never going to get into the caches. So you are never going to pollute the caches, right? So this is just one example, or to the extent that hardware is starting to be aware of this data movement and using accelerators to actually do this. Now, of course, in the case of Oracle, they don't do this with an FPGA, but there are research proposals. There is, for instance, work from Andrew Chen from University of Chicago. They have a system called Accorda, that they published a couple of years ago at BLDB, where they actually do something similar with an FPGA. Essentially, they put an FPGA on the memory bus, and they use the memory bus to actually push filtering and so forth. Now, what you do with this? Well, this is the standard in-memory, or actually, let's call it near-memory data processing, right? Where what we're doing is that we are putting processing capacity close to the memory to process the data where it is, as opposed to actually moving the data back and forth between the memory and the processor. Okay, so this is just one example of developments in hardware that we are seeing in there. And as I said, the way Oracle has implemented this is on the chip. There are people who are actually exploring how to do this by putting an FPGA somewhere along the memory path that you have in there. And I'll give you an example of how to do this later on. Now, second proof, if you want to, right, of what is happening. This is in the data center. This is no longer in a single machine, right? So in the data center, let's take the same query. And what happens is that you try to run this on a system like Amazon Redshift, which is a very large analytical database that Amazon provides, then you're going to suffer from the same problem that I mentioned before. You're going to read the whole table just to select one tuple. Except that in the cloud, you're reading this from, in the case of Amazon, you're reading this from S3, you're going to the network, you're bringing this to one compute node, and so forth. So this is going to be even more expensive than it was before, right? I mean, you will read the table from cloud storage, you will bring it all the way to the local memory, then to the CPU registers, and then you throw everything away, which of course, it doesn't make any sense. You create the same bottlenecks that we discussed before, plus you're actually creating bottlenecks in the network and on the storage, because you're actually getting all this data from storage, and you are really not interested in most of it except one tab. So Amazon has just come up with something that is called Aqua, and I give you the pointer in there, but actually you can just Google for it. Now, this is actually much closer to FPGAs, and this will be, for those of you who are interested in FPGAs, this will be an interesting development. What Aqua is SSDs attached to an FPGA, which is attached to a SmartNIC, the SmartNIC that Amazon has, right? And in essence, they do exactly the same thing that Oracle is doing with this memory accelerator, but instead of doing it in memory, they are doing it on storage. So Amazon Redshift, which is a database, whenever it runs a query, what it does, it actually uses the Aqua layer as a caching layer. So initially, of course, the first time you go all the way to S3, and then you get the data from S3, and then from S3 eventually goes to the Aqua layer nodes, is stored there, and then data go to the compute nodes. And of course, the Aqua layer is an intermediate layer that is much faster because it uses SSD as opposed to disks, which is what S3 uses. And then actually just retrieving the data is faster. But what is interesting is that they use the FPGA to be able to push down processing to this caching layer. The same thing that I said before. You can actually push selection, you can push projection, you can push, I think you can push joins, you can push regular expression matching, and a number of other things in there. And again, the point of why this is being done is actually to reduce the amount of data that needs to be moved from storage or from this caching layer to the compute nodes. And I hope that this convinces you that if people are willing to go all the way to implement a processor with this capability, or in the case of Amazon, they have a whole caching layer with this type of capability, that the problem of data movement and filtering things in place is a real one. And of course, this actually leads to a number of interesting things, like in storage data processing, where you see this more and more in the cloud, that storage is not just a passive component, but actually has quite a lot of processing capabilities. And in many cases, this is being done with FPGAs. You also see a very heavy use of caching layers, because going to this storage is expensive, takes time. So these intermediate layers are something like Aqua. They use SSD, but also people are using memory. That is the example that I will show you from our own work later on. Okay. And then there are a number of other things that are affecting how we deal with data and so forth that I'm not going to cover here. All right. Okay. So, and now let me give you one final example. This is actually something a little bit older, has been around for quite a while, but now it is part of Microsoft Azure Cloud, where they actually have an FPGA to implement a SmartNIC. You see there here in the picture, this is the latest version that they have published, where they have an FPGA. The FPGA does not really implement the NIC. There is an ASIC that actually implements the networking part, because that is a relatively stable component. But all the traffic from the CPU goes to the NIC, and from the NIC to the FPGA, and from there it goes out to the top of the rack switch. Okay? So in essence, every machine in the Azure cloud is using a SmartNIC where all the traffic is going through an FPGA. What do they use the FPGA for? Well, my understanding is that they use it right now mostly for implementing network virtualization functions. That was the original use case. But if you look for the papers that they have been publishing, now they use it for a number of things. They use it for machine learning, they use it for key value stores, they're using it for a number of applications that go well beyond network virtualization. Okay. Now, for those of you who are interested in the architecture aspects, why will Microsoft go and put an FPGA in there? At least, and I'm just repeating what Microsoft has said in a number of talks, right? I mean, over the years. Well, the interesting thing of putting an FPGA in there is that there is a lot of functionality these days that is evolving very quickly. And it is evolving so quickly that you can not really put it on an ASIC, because if you put it on an ASIC, then you cannot change it. Developing an ASIC is expensive. And it is very, very difficult that eventually this will be part of the processor, because you just need to wait until next generations, and developing processor has a much longer life cycle. If you have an FPGA, you in essence have reconfigurable hardware that you can actually program and tailor for whatever task is it that you want to perform. One of the things that Microsoft has done, for those of you interested in machine learning, is, for instance, they have implemented low precision integer arithmetic processing in the FPGA. Again, this is something that you cannot expect the processor to provide. GPUs start to provide it now to a certain extent, but Microsoft was able to come up with their own number representation for low precision numbers, and then put a processor for that on the FPGA. And this actually, in essence, allows them to build a fully customizable, so to speak, computer, right, as part of their cloud. And of course, they see this as a serious competitive advantage, right? So as a complement to near memory processing and smart storage that we have seen, the other thing that this implies is that we have a SmartNICs. Okay, so data can be processed on the fly as it goes out to the network if you have a sending SmartNIC, or as you receive the data in a machine. If you have a receiving SmartNIC, then you can actually do data. You can do things to the data as it moves around the network, right? So this notion of in-network processing is also becoming increasingly more expensive because of the data movement, but also because people realize that if data moves back and forth, you might as well do something interesting with it as opposed to just move it from one place to another, right? And this is also something that we are seeing an increasing amount of interest in things like SmartNICs. Okay. All right. Very good. Any questions? Anybody so far about these systems? All right. I see people swinging their heads, so I take that as a no. I don't see any questions in the chat, so I will continue. Now, if you are doing research, especially in academia like us, these developments are very, very exciting. I mean, we have been working with FPGAs for more than a decade. And let me tell you, 10 years ago, if you went to people and told them we think that FPGAs are going to be used everywhere for running all this functionality, people will have told you you're crazy. This is just not going to happen, right? I mean, FPGAs at the time, they were very niche hardware used for very particular applications, and they were by far not deployed at the scale that they are deployed today. And as these developments show to you, they are becoming a very, very important part of the computing fabric that we have in the cloud, right? But there is a bit of a problem here. Interesting as it is, whenever we talk about GPUs, everybody understands how is a GPU, where the GPU is, and how to use it. These examples that I have shown you demonstrate the great flexibility of the FPGA. You can actually use it for near memory processing. You can actually use it for near storage processing. You can use it for a SmartNIC. And then there are many other examples, many other places where you can actually put an FPGA. Now, the problem is that these are all very different architectures. And if you are in academia, what are you going to do about this? Because the problem is that it is very difficult to explore all these different architectures, right? I mean, so you don't necessarily have access to a processor that has this type of functionality with an FPGA embedded on it, right? I mean, or you do not have a full SmartNIC. Now they're starting to appear. Xilinx has one, the competition also has one, and so forth, right? But these are very recent, right? I mean, so again, you are not Microsoft that has the capability of developing your own SmartNIC. with a fully programmable FPGA to do whatever you want, right? I mean, so if you're in academia, you're a little bit having a problem because you do not necessarily have access to all these systems. So just very quickly, I'm going to tell you about a project that we have here at ETH where we are trying to sort of create a platform first for ourselves, but also for other people, because everything is open source and we are making it available. A platform that we are building to actually address this particular problem and keep the examples that I have just mentioned in mind, right? So the platform is called Enzian, and we have a couple of publications, one that is a bit older, the first one that you see in the slide, right? I mean, that was published a couple of years ago. We have a very recent one in ASPLOS this year that will appear in March, but the paper will be available in a couple of days. So if you're interested, I can make it available to you if you want to just write me an email, right? But what is Enzian? Well, Enzian is something that we have built for doing research. We are not claiming that this is something that is going to be used commercially or that even makes sense commercially. But what it does, it actually couples a relatively large FPGA. This is a Xilinx FPGA, one of the large ones, similar to the ones that you have on the Alveo cards. And this is together on a 2-socket system, together with a ThunderX ARM processor, server scale, 48 cores, right? And the features that we have in there are very interesting because these are the features that typically you do not find in commercial systems, right? So for instance, on the FPGA, we have half a terabyte of memory, okay? So this actually starts allowing you to run large-scale systems on the FPGA, which typically you cannot do with commercial systems. Now, FPGAs today are starting to having more and more memory capacity, but definitely not half a terabyte. And if you have half a terabyte and you come from the data processing world, as I do, things become interesting because now you can actually think of putting the entire database on the FPGA. Now you do not need to go back and forth to the CPU. You do not need to put the data on the memory of the CPU and then having to go through PCI and so forth. Everybody knows it's a bottleneck, right? So that is, for instance, a major thing. The other one is that we have 400 gigabit ports for networking on the FPGA. The reason why we have done this is because we want to explore what will happen in the future when the network bandwidth will continue growing. Now, of course, many data centers already have 40G. They're moving very quickly to 100G. People are already talking about 200, 400, and so forth. And that will actually change the way we look at computing because the network is starting to become as fast as the interconnect that you have in multi-core machines. And in some cases, even faster than things like PCI. Okay. So having these 4 ports actually allows us to have a lot of bandwidth coming into the FPGA and explore advanced designs. Another final aspect, I don't want to spend too much time on this, but another final aspect that is interesting is that we have developed our own cache coherency protocol between the FPGA and the ThunderX. This actually goes up to like 30 gigabytes per second, or gigabit, 30 gigabytes per second. Of course, this is the nominal capacity. We're not going to get anywhere near that. But what we get is comparable and favorably comparable to the performance that you get to existing systems, especially with PCI, with the addition that if you want to, this can actually be made cache coherent. So you can actually go and put data directly into the L2 cache of the ThunderX. And that, when you take all these things together, that creates a very interesting platform for exploring all these designs that I have mentioned. So for instance, if you want to do near memory processing, like this Oracle system, what you do is you put your data on the memory of the FPGA, and you use the FPGA as the advanced memory controller or advanced direct memory access controller, where you actually can push things like selection, projection, and all those sort of things to actually process the data close to memory. Okay, and because we do have a connection that is cache coherent, this actually behaves almost like what you will have in a processor. Now, it's not exactly the same, but the performance bottlenecks that you will have in such a design can actually be, you can actually design around them, and you can actually factor them in your calculation. So you can actually go and try to explore what will happen if you will have this type of near memory capacity. If you want to do something that is closer to smart storage, that's the example that I'm going to show you in a moment. You can actually use the memory, the FPGA, and the network to actually provide either main memory as a resource. This is what is called disaggregated remote memory, or you can actually use the non-volatile memory that we can actually plug into the FPGA, and then use the FPGA to just put this non-volatile memory directly on the network to actually have a smart storage. Again, the same thing. If you want to implement something like Aqua, you could actually do it. You can put MVMs, you can use the FPGA, and you have something like Aqua right away. Okay. And if you want to use a SmartNIC, then this can also be used as a SmartNIC, and this is trivially, you can see trivially how this is done because we have all these connectors that we have on the FPGA. Okay. Now, Enzian actually exists. This is not a paper design. We have already 8 of these machines, and we have ordered a few more that will be here this year. They're in the process of being put on a rack. We already have quite a bit of software and designs for the FPGA and so forth, right? I mean, so this is actually up and running. So I'm not talking about a project that will come up in the future, but this is already up and running. And as I said, if you're interested in this type of platform, please contact me because we are interested in people actually using it, right? This is what we build. And the status is that it is actually open source, both the hardware and the software, except a few things where we have done them under NDA together with a couple of companies. But most of everything that is on the FPGA is open source. And we have been building a number of tools and systems that we are also making available so that people can actually start doing research at a bit larger scale. As opposed to just using an FPGA for accelerating a particular algorithm, we want to encourage people to try to really think in terms of systems, large scale systems. And this is why we have this cache coherency layer, but we also have network stacks, we have an RDMA stack, we have a TCP/IP stack, we have an operating system on the FPGA, so shell, that I'll tell you a little bit about it, what we do in there that is different from the commercial shell. And we do have a number of examples and things that are already running in terms of data processing and so forth. Okay. All right, so this is Enzian. This is the type of platform that you can actually use to explore all these different things. And then what I want to do in the last 15 minutes or so that we finish on time for people to ask questions or discuss, right? I mean, or address any concerns or comments that you might have. Let me give you an example of a bit of a larger scale system that we have built with FPGAs. And this is an example that we have built in part with Enzian, but mostly with the XACC cluster, right? That Xilinx has donated, and that I believe that has already been mentioned and explained to you. Okay. So let me start with a number of the things that we have as components, right? And the reason why I want to talk about these components is not so much to talk about the work that we have done and how great we are and so forth. I want to sort of mention these things because a lot of these things were actually missing. They were not available for FPGAs, and this is actually a problem whenever you try to build large-scale systems. If you're trying to do things in software, you have a lot of libraries, you have a lot of open source software, you have a lot of tools that you can actually use that make your life very easy. And this is not true, on FPGAs. So this is why we have put a lot of effort in creating a whole ecosystem of tools and protocols and things that actually allow you to build large-scale systems without having to build everything from scratch every time that you start. So component number one is we have a SmartNIC that works at 100 gigabits per second. And this SmartNIC, we have it can do TCP/IP. I'm not going to talk about that one. The interesting one for the purposes of what I'm going to present now, what it does, it runs RDMA, remote direct memory access. What is RDMA? RDMA allows you to go through the network and actually access the memory of a remote machine directly. You're not going through the CPU, but you can go through the CPU. It depends on the primitive that you use. But just for us to understand the advantage that it provides, it actually allows you to go directly from the NIC to the memory, and you don't have to use the CPU if you don't want to. Okay, so RDMA is increasingly be used in the cloud, and it's increasingly be used for large-scale system because it actually saves you a lot of time. It has much lower latency than what you have with TCP/IP, and it actually does not consume that much capacity on the CPU on the remote side. Okay. So what we have done is that we have taken RDMA, we have implemented an open source stack that you can actually use as well. We have implemented on an FPGA, and then we have added processing capacity to that stack. And what we do is that the similar things to the ones that I have presented before that Oracle was doing in memory, or that Aqua Amazon is doing on the system Aqua on storage, we actually do it on the SmartNIC. So for instance, the figure that you see in the slide, right? I mean, what it does is what it takes to actually read a remote object, right? I mean, through a strom, compared to using just a standard RDMA. And then you see that actually a strom is very, very comparable to the latency of reading an object using a standard RDMA with a commercial NIC. So in essence, what we have is something that allows you to sort of use RDMA, like if you will be using, for instance, a Mellanox card, but with the addition that you have an FPGA where you can actually put processing in there. And so things that we can do is, for instance, we can traverse linked list. So if you want to traverse a linked list, what you do is you actually call the remote SmartNIC, and the remote SmartNIC will traverse the linked list and get the item that you want and then send it to you. With that functionality, you do not need to go back and forth through the whole list, navigating the list remotely, because that actually becomes very expensive, right? The same thing with hash tables. Hash tables have collisions. If you have a hash table and you're actually accessing a hash table that is remote, if you do not have this type of SmartNIC functionality, every collision means that you're actually going through the hash table, you're going through the network, you're getting a value, it's a collision, so it's incorrect, it's the incorrect one, so you have to go back again until you actually find the one that you want. And again, a SmartNIC can actually do this for you, and then you are minimizing the number of network round trip times that you have in there. So a SmartNIC is in place, allows us to do 100G RDMA to memory. Okay, so element number one. I'm going to skip this just in the interest of time. The second one that I want to sort of tell you as a component for what I'm going to present at the end is Coyote. What is Coyote? Coyote is, we call it an operating system for an FPGA. That is a little bit of a grandiose name that is good for a paper. But between us, what this is just our own shell for the FPGA. What is interesting about Coyote is that it actually, what it does, it tries to, and the reason why we call it an operating system, it tries to turn the FPGA in something that resembles as much as possible a normal computer. Whenever you start a normal computer and has an operating system, you do not need to worry about the network. The network works, you have the drivers are there, and programs can actually just use sockets to actually go through the network and so forth. This is not the case on an FPGA. Typically, if you want to use TCP IP or you want to use RDMA, somebody has to give you the driver, somebody has to put it in there and so forth. And actually, this is complicated, right? I mean, that assuming that you have an open source stack to actually use, right? The same happens with accessing the memory on the host, right, of the machine and so forth. So what we have done with Coyote is a shell that has networking already implemented in there. So you just deploy the shell and then you have networking. We have provided a very simple interface to that networking, so you don't have to worry about that. It also provides a unified memory space, the host FPGA, because it implements virtual memory between the FPGA and the host. So the host sees the memory of the FPGA and the FPGA sees the host of memory, the whole memory, as much as you want to, right? I mean, with no limitations. And everything is done using virtual addresses. So in essence, what Coyote does, it implements virtual memory addressing and everything that corresponds to it, right? I mean, with TLVs and all that stuff, so that the FPGA now becomes one element more in the computer, right? I mean, where you don't have to do all these translations yourself. And the other interesting thing that, of course, this was critical for many of the applications that we have in mind, is that it actually provides you several regions, several reconfigurable regions, where you can actually go and deploy your own logic. This is what we call the user logic. If you look at the figure, we have put up to 10 regions in there. Now, of course, the more regions you put, the smaller they are and so forth, right? I mean, there is a clear trade-off in there. But for the experiments that I will show later on, right, I mean, the system that we have built later on, we use 6, but in principle, you can put up to 10, right? And again, what Coyote does is that this is all automatic. You do not have to worry about it. All those regions have access to memory. The memory is isolated. So if the memory that one region is accessing is not visible from the other one, the same thing that you will have with threads or with processes, right? I mean, in a CPU and so forth. The same thing with networking. The network is multiplexed across these user regions, and all the resources that are available are automatically multiplexed, right? So this is a way to actually provide a number of different processes, what we call virtual FPGAs, but think about it in terms of processes from a CPU perspective, with a number of features that you expect to have in a normal computer. Networking, access to memory, access to the whole memory, and so forth, transparent use of virtual memory, and so forth. Okay, so we have a SmartNIC, and now we have something that resembles an operating system running on the FPGA. Okay, so what we have done with this, we have implemented a smart disaggregated memory. It's a system that we call Farview, and we have presented this very recently at a conference called CIDR, right, that took place a couple of weeks ago in California. And this is what the system does. For those of you who maybe might not be entirely familiar with disaggregated memory and what is happening in this area, in the same way that in the cloud you disaggregate compute and storage, so the disks are not on the same machines as where you compute, they are somewhere else, and then you have a network in between. People are proposing to do the same thing with memory, with DRAM, right? I mean, so you actually do not rely entirely or solely on the memory that is on the compute node, but you actually provide disaggregated memory, DRAM, through the network for a pool of compute nodes. Okay. So what Farview does, it actually implements this smart disaggregated memory using a SmartNIC, our SmartNIC, using Coyote, and using the memory that we have on those machines to actually provide the smart disaggregated memory to compute nodes across the network. Okay, so how does it work, or how is this used in practice? Let me go back to the use case that I told you at the beginning that I was keeping in mind, that is databases. Now, again, bear with me if you're not familiar with databases. Databases actually are very nice for this type of work because databases have a very structured workload. What you see on the left side of the slide are SQL statements that are doing something with two different tables, selecting different attributes and so forth, and doing a join between them. What you see in the middle are two trees. These are what are called the query trees, the execution trees. So that SQL statement database will translate it into that execution tree that tells you in which order you have to do these operations. The lower operations are typically called access methods. They have projections, selections, and so forth. And they select the data and then pass it on to an intermediate operation. In this case, in both cases, it's actually a join that actually combines these two streams of data, if you want to, into the final result. Okay. So what we do with the disaggregated memory is that in a database, typically the way you will do this is that you will actually look for these tables, as I told you earlier on. You will grab them from storage, bring them into memory, and then you will do the selection and projection. With the selection and projection, you take the data and you move it to the space of the query, what is called the server process, and then the server process will actually continue and do the join and so forth, right? So what we're doing is we are replacing all the system part of the memory that you will have in a database engine with remote memory, and with the capability of actually pushing projection, selection, and a number of other operations to that remote memory. Okay, so whenever you want to run a query, now you do not need to bring the whole table to your compute node. What you do is you actually push down part of your query tree to the memory. Most of it is executed on the memory. And then the rest, what cannot be done in the memory because there is no room, or because it's not convenient, or because it's not efficient to do it on the memory, then you send it to the compute node, and the compute node takes care of the CPU-heavy operations. Right? So what do we gain by this? We gain by this reducing data movement. We actually do near data processing, near storage processing, and we actually provide a very new architecture that actually provides, as I said, disaggregated memory. This is not just disaggregated storage, but this is disaggregated DRAM, that of course has a much lower latency and has far higher bandwidth than typical storage. Okay, so how does it work? Well, as I said, since we run Coyote in one of those FPGAs that is providing the disaggregated memory, we can actually use the different dynamic regions that we have to actually serve different streams. So you can have in Farview until now we have tried up to 6. So you can actually have 6 users or 6 programs that actually are retrieving data from this memory. What we can put on those regions, we can actually put a number of operators. We can put projection. What it does, it actually removes attributes from the table. We can put selection. What it does, it matches the tuples against a particular predicate. We can do very simple selections like is greater than or equal than and so forth, but we can also do regular expressions, which are much more complicated. Regular expressions are used, for instance, for text. And then we can also do things like group by, distinct, aggregation, and so forth that are more specific operations that you find in a database. For instance, group by, what it does, it actually takes several tuples and aggregates them together. Distinct eliminates copies, so you will get only one copy of one particular tuple, right, if there are several copies, and so forth, right? So all those operations can be done in the memory, so to speak. And then we can also pack the data and we can send it in the same way that we can actually encrypt it, decrypt it, we can encode, decode, and all those sort of things, right? And this is all done through the tools that I have mentioned before. We have now the SmartNIC that allows us to do this through RDMA. So whenever the remote node, the compute node wants the data, it is not only that it's requesting the data through the network, but actually once we request the data, we can actually go and put it directly into the network, directly into the memory of the compute that is actually making this request without involving the CPU, right? That is one aspect. The other one is that we can actually sort of, as I said, we can actually push these operations close to memory. And by doing that, we actually significantly reduce the amount of data that moves back and forth. And as I told you, we can actually have several dynamic regions active at the same time. So this doesn't work only for one application, but we can actually have many different applications accessing this memory at the same time. Okay. Let me just give you a very simple example, just to sort of finish on time, right? I mean, so that we can have time to discuss. Where I show you a little bit what is the advantages of this design. What you see on top is a very simple operation for disaggregated memory, where you have a compute node that requests data from the disaggregated memory and just reads the data. And the other one is that we take advantage of Farview to actually read encrypted data, decrypt the data, and then send the decrypted data to the compute node, right? In a normal architecture, you will expect that the second configuration, where you are decrypting the data on the fly before you actually send it to the compute node, you expect that to have higher latency and potentially even lower bandwidth, because the decryption can actually get complicated. This is not true in Farview, and it's not true because we are using an FPGA and we're taking advantage of the huge parallelism that is on the FPGA. So what you see here is that the black line is an RDMA read, and then the red line is RDMA read through Farview, plus decrypting the data as we are reading it from memory. So we are reading the data from memory, we are decrypting it, and then we are forwarding it through RDMA directly, and you see that the bandwidth is exactly the same one, right? This is the big advantage of FPGAs. In case you have not heard this before, the big advantage is that FPGAs allow you to process data at line rate. You're processing things in a bit of a pipeline configuration. You're actually processing things at the speed that they can actually go to the network, and this can be done for many different operations. And this is a huge advantage because neither CPUs nor GPUs can do anything like this. You will need to bring the data to the CPU and then process it there and then get the data back to the network and so forth. And only on that operation, you're going to lose a huge amount of performance. I don't want to spend too much time on this because there is a paper that you can read, or you can ask me about it and I can give you more details, right? I mean, but we have actually compared Farview with a number of baselines with a buffer cache implemented. Buffer cache is the component of the database that actually stores the data, right? I mean, implementing in local memory with processing on the local CPU. We have implemented a buffer cache using a Mellanox NIC for using RDMA. And then we have actually compared this with Farview, right? And what you see is that for a bunch of different queries, so for instance, the one that I'm showing right now is a query that has 50% selectivity. It actually selects half the data. You see that Farview, and there are two versions of Farview. Let's not get into that, what they are. Farview has a much better response time than even reading data from the local memory, right? Okay. The same one if we're doing a group by query with aggregation, right? I mean, Farview is much faster because we're actually reading data from memory, we are aggregating, and the amount of data that we are moving, whether through the network or the memory bus in the computer, right? I mean, it's much less, right? And of course, Farview has a much faster response time. And the same way, the same happens if you actually try to use 6 concurrent clients. So this is not just for one single machine, because you can actually claim, well, yes, you're using the whole FPGA for one single client, but then this memory is not useful for anybody else. But as I said, we have actually tested it up to like 6 concurrent clients, and the 6 concurrent clients can actually get a very fair share of what is in there, right? So this actually works. It's very useful. And I hope that it gives you a good example of what you can actually do with FPGAs today to actually explore this space, right? Of course, now for the next step for us, and this is why I also mentioned Enzian, is that we want to put this in Enzian. We actually want to test this with higher network bandwidth, also with a much higher memory capacity, because we can actually put up to half a gigabyte in one of those things. And once we have a cluster, we can actually go and have about 4 terabytes of disaggregated memory, smart disaggregated memory, and start building systems that are relatively large scale and see what happens in practice with those systems. Okay, so I want to finish with this. The point, since all of you are here to learn about FPGAs and so forth, the point I want to make is that hardware acceleration and specialization is here to stay, and FPGAs are playing a huge role in this, right? So there are a lot of bottlenecks and inefficiencies caused by data movements, and through the examples that I have shown you from industry, but also I hope through the examples of our own research, right? I have shown you the role that FPGAs can actually play in actually addressing those bottlenecks. And because they are so effective at it, one can expect that you're going to see more and more FPGAs being deployed in data centers and the cloud. Okay, so let me conclude with this. I'll show you here a picture that I assume you have actually seen already. Mario can confirm this, right? I mean, about the XACC cluster that we have here at ETH. What you see in the picture is the cluster that we have been using for the last year and a half, almost 2 years. And very soon we are going to have another 10 nodes with U50C boards that have high bandwidth memory. They're also large FPGAs. They're almost equivalent to the 280s. So in that regard, they're very powerful. And we're very excited to have then a cluster with 20 FPGAs that will actually allow us to try systems like the one that I have presented at really very large scale. Okay, so I finish with this. Thank you.